In the next few videos, we're going to talk about kernel ridge regression. This is one of the largest conceptual jump for this entire series, so we're going to take things a little bit slowly. And remember last time when we derived the solution for multidimensional span, in the end, we have a linear system like this. And here I'm just going to make one small simplification by removing the polynomial term. So let's say that alpha equals to 0. That's when we don't have any polynomial term in it. We can just write out the first equation as k plus lambda I c equals to y. So this time we are going to show how this equation arises from we'll see. So today we're going to see how this equation arises from the ridge regression. This is coming from the ridge regression on feature space. Also, just to write out f of x, we can do it like this. So f of x equals to summation I k x xi times ci. So that is the solution we will have for the function f, for the nonlinear function f. And for this function f, we'll also show this is a linear function in the feature space. Okay, so that is the goal today. Okay, now let's go through the problem setup. So our data are paired data xi, yi, with I go from 1 to n. And then the xi, let's say these are d-dimensional vector or d, and then yi are real numbers. And now let's just expand this problem a little bit and then define a feature map phi. So phi is a feature map, and that gives us phi of x. Let's say phi of x is a m-dimensional uh, m-dimensional vector. This is just as our feature expansion formula, right? For example, the phi can be the quadratic map, like this, 1 x x squared, right? So this is just a feature. This is just a basic expansion formula. Suppose x is a vector, then we can square it, right? As one additional feature to the system. But in general, we can do m-dimensional. So this is still a finite dimensional feature map. We're just expanding it into m-dimensional vectors. For the next few videos after this, we're also gonna look at the infinite dimensional map, right? Whereas phi x can have infinite dimension. So in the future. But here, let's just consider the finite case to make our life a lot easier for this video, and then we are going to translate everything from finite to infinite. That is one of the biggest conceptual jump, I would say, for this kernel ridge regression. But now let's just look at phi to be finite, m-dimensional, and then we can also define the matrix form, the capital Phi. Uh, it is a R m by n matrix, n by m matrix, I think. Yeah. So n by m matrix. And then if we write it out, phi will equals to phi of x1 all the way to phi of xn. Remember in our basis expansion, we are solving this as a linear system, right? So we are solving this regression problem. So it's going to be phi beta, and let me just write it out as the norm. So we minimize this over beta. So that is the objective function we have for the basis expansion formula. That way the fx equals to phi of x equals to phi times beta. Or I should say this, it should equals to phi of x times beta. This is a nonlinear function in X. It's this function is nonlinear in X, but linear in phi of X, right? So once we expand its feature, the problem becomes linear again in that feature space, but it's not linear, it's nonlinear in the original space. So that is a problem we are dealing with. And so this time we're just going to expand this formula a little bit into a ridge regression problem. And let me just say that. And so here, this is a problem for basis expansion. OLS. And for the ridge regression problem, we just have one additional term in addition to that. So ridge regression, we just consider this, minimize beta, and then y minus phi beta 2 norm plus lambda beta 2 norm. That is a ridge regression. Um, this is a ridge regression. So we are adding one more term to it, right? So this beta, the 2 norm of this is called L2 penalty. The ridge regression is also just a common technique, common method in statistics and machine learning to reduce the variance of the estimator. We also see that along the way, in our kernel trick derivation. So now let's just solve this problem. And to solve this, we're just going to take the derivative. Let's call this function L. So let's define this as function L, and then we just do the derivative of L, the gradient vector, gradient with respect to that. And then let me just write out the matrix multiplication form. That's easier to deal with. So L of beta equals to y minus phi beta transpose y minus phi beta plus lambda beta transpose beta. And then we just do the derivative, and this is equals to 0. That give us phi transpose minus phi transpose times 2 minus phi beta plus 2 lambda beta equals to 0. And we cancel all the 2. We have minus phi transpose y plus phi transpose phi beta plus lambda beta equals to 0. So we have phi transpose phi plus lambda I beta equals to phi transpose y. So this is a normal equation we have in the end. And so this is a normal equation of ridge. And if we compare that to the normal equation of the ordinary least square, so this is so we just have one additional term, the lambda I added to the to this matrix there, right? This is the equation for OLS, and we just have this one additional term of lambda I there. But that lambda I term is actually very important, right? If in one case that suppose that our phi is n by m matrix, right? So this is m by n, and then this is n by m, right? So that gives us the phi transpose I phi as m by m matrix. And sometimes if we have more features than our data points, that means this phi transpose I phi may not be invertible, right? May not be full rank, and this is not full rank if n is smaller than m, right? So that can happen when we have a lot of features. And but however, we are adding this lambda I to the ridge regression problem so that this system can always be solved, right? So if it's not full rank, then that means this okay, so that's if it's not full rank, that just means that we cannot invert the matrix, right? We cannot do this. We can just not invert the matrix. But also that in terms of the geometry, it means that there are more ways, there are more data points than the number of equations when we want to solve this linear system. This is the case when the system has not don't have unique solution. So this is not a unique solution. Or I can say just there are infinite many solutions to the linear system. But for the ridge regression, once we added the lambda I, it is always revertible, right? So ridge for the ridge, and we'll have phi transpose phi plus lambda I inverse is invertible, right? Because this is full rank once we added the matrix lambda I onto it. So this is always that means ridge always have a unique solution. Okay, so that is one of the main motivation for people to invent ridge regression is that they can always have one unique solution when there are more features than the data point. And also the other thing is that sometimes even when you can solve the problem, even though phi transpose phi is full rank, we sometimes still want to use ridge regression to stabilize the solution, right? This is happens when the matrix is barely invertible, right? So that means it has just very small eigenvalues. And even though we can invert it, but that doesn't mean the solution is stable. It means that once if we tweak the system a little bit, then the beta parameter can change a lot, right? So that's why that's another reason we want to use the ridge regression to just stabilize the system. Okay, so for the next part, let's just derive the kernel trick formula for the ridge regression. And so the tool we are going to use is singular value decomposition. And then we are also going to just look at the ridge regression shrinkage, the spectral shrinkage of ridge regression along the way. Okay, let me copy this equation. All right, now let's go through a few key facts about the SVD. We are going to do the SVD on the matrix phi. Here, phi, remember the dimension of that is n by m matrix. And then you can write out phi equals to u sigma v transpose. And the dimension for this, u will be, let's do the general case. This will be the n by r matrix, sigma will be r by r matrix, and then v will be r by n matrix. This means that the rank is r. So the rank R matrix for our matrix phi here. And then we also have the U matrix to be orthogonal. These are singular vectors. So U transpose U, sorry, I think not U transpose U transpose U equals to identity, and then V transpose V also equals to identity. And the sigma matrix will have all the singular values in it. So it's sigma 1. It's a diagonal matrix to sigma r. So that's our diagonal matrix. And also we can also write out the form of the eigen decomposition. So our phi transpose will become U sigma square U transpose. And then phi transpose phi will become V sigma square V transpose. And so importantly, for our kernel matrix, right, we will later show that we can define that as the K, right? So phi transpose. So that will become the kernel matrix later on. And then so to see that, you will also see that Kij in this way will be the inner product of phi xi and phi xj of the these are two data points. These are data points in Rm, and so that will be just be the inner products between these two data points in their feature space. Okay, so now let's just plug in the SVD formula for the beta height, and so that's what we're gonna do. So what we're gonna do next is just plug in SVD for beta height. And our beta height will become, uh, so it's V sigma square V transpose plus lambda I inverse, and then V sigma transpose U transpose Y. And then, so for the lambda I here, we can decompose that as this is equals to V times lambda I V transpose, right? And then we can merge these terms together as V sigma square plus lambda I V transpose inverse V sigma is diagonal, so it's symmetric U transpose Y. Okay, so this matrix here is very easy to be inverted, right? We can just invert a diagonal matrix in between, right? So this gives us V sigma square plus lambda I inverse V transpose, right? So that's going to be the inverse of this. If you just multiply these two together, then this V or everything will just cancel to I identity, right? So that's going to be the inverse of that, and then so let's keep going. This is V. Just remove this. So it's going to be V sigma square plus lambda I inverse V transpose V sigma U transpose Y. Then these two cancels to identity. And what we have in the end is just V sigma square plus lambda I inverse sigma U transpose Y. Okay, this is nice. And because these two matrices in between are both diagonal matrix, we can just expand it, right? So these are diagonal. So we can expand it. So it's going to be V times this diagonal matrix as sigma 1 over sigma 1 square plus lambda all the way to sigma r square plus lambda U transpose Y. Okay, so that is a nice formula for the ridge regression. And this is also called this is from here, we can also see the shrinkage of our estimator. And this lambda term here is called the shrinkage factor also. This is the lambda is also the shrinkage factor. Because for the ordinary least square, if we write out the same formula using SVD, we just won't have this lambda, and everything else will be the same, right? So that means this is this is a spectral shrinkage where we add the lambda to all the singular values to make the estimator smaller. And here, if you if you go on another path to look at the bias and variance trade-off, and so that's also the equation to use, right? So so the bias variance trade-off can be seen this way as well. Right, so the bias is defined as the expected value of beta hat minus beta, and then the variance is just going to be the variance of beta hat, right? So so if you plug in beta hat here, that you can compute the bias and variance for the ridge regression and compare that to OLS, we'll find that the uh, ridge estimator is biased, but lower variance. And the OLS will be unbiased. Unbiased just means the bias equals to zero, but higher variance. So that is a bias variance trade-off for the ridge regression that can also be obtained using the SVD formula. But that's not our goal here. Let's just be focused on how to get a kernel trick out of this. Okay, yeah. So let me just copy the formula to the next page. Okay, now let's focus on our goal and see how kernel trick pops up in this ridge regression formula. So next we are going to look at is y hat, and that's our f. That's also our fx equals to phi beta hat. And then now we're just gonna swap out the phi with SVD formula, and then that becomes U sigma V transpose, then V sigma square plus lambda I inverse sigma U transpose Y. And then we'll have V transpose I, V equals to identity, that cancels. And then this gives us U times sigma square plus lambda I inverse sigma U transpose Y. So all of these are diagonal, right? So that means you can freely swap in their orders. So diagonal, we can swap their orders, and then it become U times sigma square, and then sigma square plus lambda I inverse U transpose Y. Here we can also expand this whole thing out as sigma 1 square over sigma 1 square plus lambda, also sigma r square plus lambda, U transpose Y. So here we can see the same shrinkage factor applies. And if we do the ordinary least square, then this whole matrix, diagonal matrix, goes to one. This goes to one if lambda goes to zero, right? So this is the OLS, and we won't have this shrinkage factor for this closed form y hat, right? So that can be interpreted as a projection, right? So that means when we are projecting it, we cannot project it on a reduced space given by the spans of the singular vectors. Okay, we're not here to see the shrinkage. We're here to derive the kernel trick. We're just one step away from that. And then, so now I'm just going to insert U transpose U in between because that's give us the identity. Sigma square plus lambda I inverse U transpose Y. And here you see that the first matrix gave us K matrix, right? And this is exactly the U sigma square U transpose, right? That equals to phi transpose. So this equals to phi transpose. And the second matrix gives us, so the second one here gave us the K plus lambda I inverse, right? This is also equals to phi transpose plus lambda I inverse. Okay, this is very nice, and we already reached our kernel trick. So the thing is that we can write out the estimator, write out the linear system with respect to matrix K only, without even touching phi. So that is the essence of kernel trick. So in the end we have K times K plus lambda I inverse Y. Okay, this means our ridge regression can be written without phi. right? So that means we don't even need to know our feature map phi to write out the solution for the ridge regression. All we need is K, right? All we need is K matrix. Right, remember that Kij is the inner product between the data points, right? It's equals to phi xi and phi xj. That's all we need, right? We only need the inner product between data points in the feature space, but we don't need really need that feature map. And in the next two videos, we are going to translate this entire derivation into infinite dimensional space, into functional space where we can just operate functions as their linear algebra. This just works like magic, and everything just carries out, including the SVDs, the spectral theorem. Everything in this proof can be directly translated into the infinite dimensional version. So that's really the key reason why kernel-rich regression works. It's because we have the same spectral theorem on the infinite dimensional space, just like this one. Okay, now let's just rewrite this a little bit more. And so now we're gonna call this vector here as a vector C. So that way we have two equations, right? The first is that C equals to K plus lambda I inverse Y. And then we also have Y hat equals to K times C. Okay, this is very nice. You see that this is exactly like our smoothing spline in the beginning, right? If we just move it to the other side, right? So in the smoothing spline in the beginning, we have so smoothing spline, if we compare that, right? Well, we write it in this way, right? We have the linear system as K plus lambda I times C and plus P alpha equals to Y, right? If we ignore the P alpha, then if we ignore the polynomial term, this is exactly our kernel-rich regression, right? And then we also have the f of x equals to summation ci k x xi plus P alpha, right? So if we ignore the P alpha, and then this is exactly the same as our second formula here, right? This is our y hat. Okay, so if we do one particular point, f of xj, that gives us exactly I, ci, k, xj, xi. All right, so this is the same as one of the rows, right? One of the rows in K multiplies by the vector C, right? So these two are the same. Okay, now we see that our smoothing spline is exactly the same as the kernel-rich regression on the feature space. But here, a natural question for this is that what is the feature map for the smoothing spline? Feature map for smoothing spline. So it turns out that we don't even need to know the feature map, right? So the feature map is just going to be an infinite dimensional feature map. It's because the same math carries out, but we don't need to know that, right? So we no need to know it. No need to know the feature map. But we can still solve the problem using the kernel matrix K. So that is the kernel trick. Okay, and finally, let's just do a comparison between the explicit feature map versus the kernel trick. Because there are too many letters flying around, that's just making things crystal clear. So the first is that the design matrix. The design matrix. And for the feature map, we have the design matrix phi uh, as a matrix, as an n by p matrix, right? And for the kernel trick, we have the kernel matrix that equals to phi transpose, and that is an n by n matrix. Okay, and the second thing is for the coefficients. So the explicit feature map, we have beta, that's a p-dimensional vector. And for the kernel trick, we have C, and C will be an n-dimensional vector. So that's the difference. Let's keep going, and then we have the closed form solution. So beta hat equals to phi transpose phi plus lambda I inverse times y, right? If we use the SVD, and then for the SVD closed form, we'll have V and then sigma square plus lambda I inverse U transpose Y. And for the kernel trick, our C parameter equals to the closed form will be K plus lambda I inverse Y. And for the SVD of that, that's going to be U times sigma square plus lambda I inverse U transpose Y. Okay, so the next is that it's an in-sample prediction, right? So it's a prediction. So in-sample, let's say this is in-sample prediction. And so that means we want to predict our y hat, right? That's going to be an n by 1 vector, with all the evaluation point, right, at x1 to xn. So that's going to equals to phi beta hat. And for the SVD formula, I'm just going to write out the SVD, and that's going to be U uh, sigma, I think it's sigma square plus lambda I inverse U transpose Y, right? And then for the kernel trick, we will have Y hat equals to K C hat, right? So that's gonna give us U. This I think is exactly the same for the two, sigma square plus lambda I inverse U transpose Y, right? So you see that this is exactly the same. So that means the function underpinning these two methods are exactly the same. And so the next part is actually very important. It's the out of sample prediction, right? And that also give us a function, right? Let me just call that the predictive function. And let me just call that the predictive function. Okay, so that's our y of x, right? So this is suppose x is out of sample, right? This is out of sample, and we can write that out as phi of x transpose times beta. So for the kernel trick, and so our predictive function will become this, right? It's going to be summation of I ci k x xi, right? And so this formula works because of the reproducing property of the kernel. This is a reproducing property. And now we can show this result equals to each other. And we just bring out our old friend SVD, and suppose that we can so we just expand phi, right? Phi of x. So phi of x is going to be a p-dimensional vector, right? So that means we can express it in the as a summation of all the singular vectors, right? Singular vector j. Let's call the coefficient alpha j, right? And then to write it out in the matrix form, that equals to v times alpha, right? And then we just use the SVD formula, the closed form for beta hats, to to see like what that lead us, right? So that equals to alpha transpose v, and then we plug in the closed form for beta hat. Let me just call this beta hat. Uh, all right, maybe I call this y hat of x, right? And then that's going to be v transpose v sigma square plus lambda I inverse u transpose y. And we can cancel out this v transpose v here into identity. We'll have alpha transpose sigma square plus lambda I inverse u transpose y, right? So that's the SVD expression of it. And let's see if we can get the same for the kernel trick. And so here you can expand this K, this kernel actually. You can expand it as the inner product between phi of x and phi of xi. So and then we can write out the matrix, right? So that's just gonna be equals to that just equals to phi uh, times phi of x, I think. Yeah. Yeah, so phi is n by p, and then phi of x is p by 1, right? So that's gonna work. So, and then we have the c, and also we have the c vector, right? So that will give us, um, that's going to give us phi x transpose phi, and that's just going to give us phi x transpose phi, and then phi transpose C, right? And then we just plug in the closed form for C, and then replace phi with SVD, right? Replacing everything with SVD. Then we'll have the phi of x becomes alpha transpose V, and then we'll have the alpha V transpose, and then we'll have V sigma transpose U transpose. Then the C become U sigma square plus lambda I inverse U transpose Y, right? And then we can do some canceling again. So this gonna cancel to identity. This will be identity. And that give us alpha transpose sigma, and then sigma square plus lambda I inverse U transpose Y, right? So they are the same. Now we show these are the same, right? Okay, good. So so that means our kernel trick, our using the kernel trick, we have the reproducing property to just to get the exact same function as we have for the explicit feature map. Okay, and here's something I want to say is that for the for if you compare this if you compare the coefficient, right? So our beta lives in p-dimensional space. So what does this mean is that in our feature space we are kind of building the function, our predictive function using p independent functions, right? So so you know if you just expand it out, and then we'll have the y of x, right? So y of x is just going to equals to so here the y of x, right? What we end up having is just going to be the just going to be phi 1 of x times beta 1 plus phi 2 of x times beta 2, right? So this phi, so and all the way to phi p of x times beta p, right? So these are kind of like the building blocks, right? So these functions are like the building blocks for this nonlinear function. If we do this, if everything takes place in the feature space. And if you look at the kernel trick here, right? So our building block becomes this k function, right? So the k function is just going to be that's going to be c k of x xi times c1 all the way to summation all the way sum to k times x k of x xn times cn, right? So now we have like n building blocks using this k matrix versus the p building blocks of the phi. So that's really the key difference between the two. And the links connecting these two are the singular are the singular vectors, right? So for this function phi here, you can expand it out. You can write it out in terms of the singular vectors of v, right? So that's what it gives. And then for the k function here, we are writing it out in the singular space of u, right? So they are really kind of living in different space, but there's a link connecting the two, and that is SVD. So you know this interpretation kind of carries out in the infinite dimensional space, right? So in the infinite dimensional space, our peak will go to infinity, and then also our v right become eigenfunction, right? So v becomes eigenfunction in the inside of the I should say singular function. I should say singular function will become the singular function inside of the singular vectors. uh, in the as our finite case, right? And then our nonlinear function will be made up of a singular function v here. But to connect those two, to connect that with the data, we have to operate on the finite dimensional space, right? So that's so we'll still have the Rn for the U. U is still gonna live in the space of Rn, right? So what I'm trying to say here is that we can either operate on the space of V or operate on the space of U. And so that's really just the two different formulation of the same problem. Either with the explicit feature map or the kernel trick. And for the next video, very importantly, we're going to look at how to translate the results in the finite space linear algebra into function space, where the same mechanics still plays out, including the singular value decomposition. That is really the centerpiece for this entire derivation. So then we're going to carry out the same derivations for the function space once we have that translation.